In the last section, we went ahead and looked at how to find the derivative when we were doing the differentiability using this definition of derivative limit as h approaches 0, or actually we took the other definition, which was the limit is x approaches some value t. And same idea, what we're going to do is we're going to find out that there actually is a shortcut to this. So you don't have to go through this limit every time. What you could do, if you have the function x to the n, well, they already worked it all out here for you. Use the binomial theorem expansion here. Everything cancels out. And what we learned from this, that's long proof here, kind of an informal proof, is that if f of x is x to the n, then f prime of x is n times x to the n minus 1. And I don't know, they brought up the other notation. So another notation is just saying the derivative of x to the n, so d dx is just finding the derivative, is n times x to the n minus 1. So it's just the same statement. This is just taking an f of x approach. F of x is x to the n. So the derivative of that is n times x to the n minus 1. And then this is another approach, same idea. It's just saying, hey, let's take the derivative of x to the n, which is n times x to the n minus 1. So two different ways to state the same thing. So how does that work? Well, if the derivative of x to the n is n times x to the n minus 1, so what we're going to do is this exponent here is just going to come down in front of the x, and then we take away 1. So when we find this derivative, I'm going to bring down the 5, and I'm going to actually draw it out because I like to show you that this 5 is just going to come down front like that, and then we take away 1 from that exponent. So it was a 5, so now it's a 4. So the answer is going to be 5x to the 4th, and that's how we do this. It's actually quite simple. I mean, if you wanted to run through the long way, we would have to do the limit as h approaches 0, and we would have to do x plus h to the 5th power minus x to the 5th over h, and then we would have to literally expand that out, x plus h 5 times minus x to the 5th, cancel things out, and then in the end, it's just a long process. You can imagine how long that limit will go on for, but the shortcut is just the exponent comes down, take away 1. I don't know why the mathematicians came up with that. They probably just realized the pattern and then came up with that crazy proof there. So what about this one? You just bring down the 8, take away 1, and that's it. Look at this one. Bring down the 3, take away 1. This one, bring down the 12, take away 1, and we see that pattern. I do want to talk about what if there was like x to the 1? Well, if you take the derivative of this, you bring down the 1, take away 1 is 0, and x to the 0 is just 1. So that just leaves you with 1. The x goes away, basically. So what about if you had a derivative of a constant, like 5? And we're going to learn these rules later. Well, you can think of that as x to the 0. 0 comes down. And 0 times x to the negative 1, but 0 times anything is 0. So just a couple ways to think about that. But I think for this assignment, I don't know if you're going to run into the x to the 1. We're going to learn these rules later. But for the most part, just getting used to that whole idea, bring the exponent down, take away 1. Very